Good morning, everyone. This is Shawn, and I'm very glad to be here to share with you some of our work we have done recently. Earlier this morning, in the opening session, my colleagues have introduced quite a few new features for our product, including a few of our technical progresses we have made recently. And I'm very excited and can't wait to go deeper and share with you what we have done and how we achieved the progress. And in Agora, we have realized that the quality of experience matters most for RTC users, and we are striving to make progress so that the RTC can feel like there is no delay, no stalling, and no blur. And also, we have realized that machine learning actually helps in almost all areas in RTC. Take a look. A brief diagram of the end-to-end system includes pre-processing, followed by encoding, and then data is sent to the cloud. At the receiving end, the signal will be decoded and then post-processed before rendering and displayed. And in tasks such in pre-processing, such as beautification, style transfer, and even like noise reduction and the high dynamic range, can benefit from machine learning. And during video encoding, tasks like perceptual video encoding and quality assessment and some encoding mode decision are also benefiting from machine learning. And in cloud, it's like channel estimation, data analytics for QoE enhancement, and also content moderation are familiar ones to everyone already. And in post-processing, we can make use of machine learning to improve the detail and also the artifacts reduction. And it's been known that the best results are obtained by training some big neural network models running on big platforms using big data. And the modern RTC, however, is happening more and more on the mobile devices. And due to its limited resource on mobile devices, we are facing quite a big challenge. And it's actually very difficult to design a small enough deep learning neural network model such that it allows its inference model to run on the mobile devices in real time without causing a lot of power consumption or causing any heat issue. And secondly, the small enough model still have to give good and acceptable results. And also, due to the scarce of data, it has to be able to be trained using reasonable amount of data. And last but not least, remember the additional processing has to be on top of existing tasks, such as video encoding, decoding, and video rendering, which already takes a lot of computation resources on the mobile devices. So it has been extremely difficult. And today I'd like to share with you how we have done and how we achieved this real-time application of the deep learning using a couple of cases for case study, the video encoding and post-processing for detail enhancement. Let's go over it one by one. And first, let's talk about video super resolution. The problem is, in our application, due to the network jittering or traffic congestion, the bandwidth becomes very limited from time to time, and then we have to send lower resolution or low bitrate video across the network. So when that low bitrate or low resolution video is received and decoded and displayed, it's usually blurry using conventional scaling method. So more details and sharpness are desired. So in this example is showing like using the bicubical interpolation 2x upscaling in both directions, the result is blurry. And taking another example, this is 4x upscaling in both directions. And the picture on the left showing that very little detail. You probably couldn't even recognize its legs from zebra. Meanwhile, the ground truth shows that the stripes are clear. So in this case, the conventional method couldn't give any details at all besides the blurriness. There are scalars trying to improve this situation. For example, in iOS, there are a couple of scalars. There's a normal one, and there's a sharper scalar as well. And those methods actually is a trade-off between the effect and artifacts. And Apple knows what it is doing. In the normal scalar, the result is quite blurry. And the sharper one is a little bit sharper, meanwhile, causing a lot of halos and the ring effect along the edges. So you have to compromise. If you want to get it sharper, you need to accept the artifacts. If you want to avoid the artifacts, then you have to accept the blurriness. Super resolution algorithm actually help enhancing the details and the sharpness significantly. It's been known in industry. For us, we have been utilizing super resolution as a standalone post-processing step, which is placed near the end of the video processing pipeline before rendering and display. And the generative and adversarial network is very effective in generating details and sharp-looking details. And it is also the base of our super resolution model. And in 2014, Ian Goodfellow and Yoshua Benjo and their colleagues published their monumental work called generative adversarial nets. Since then, GAN has been very popular and is almost occupy more than half of the papers in every major AI conferences. And the idea is actually from the Nash gaming theory. And the GAN model consists of two networks, the generator and the discriminator. The generator receives as input a noise or low resolution picture, and would generate a high resolution picture, which is tempted to be looked as real. On the other hand, the discriminator is trying to tell this generated picture is a fake. On the other hand, when a real high resolution image is fed into the discriminator, as left-hand side shows, the discriminator tries to recognize it's a real data. And the generator at the next iteration would try to enhance its own capability and try to generate a better version of the fake data. In the meantime, the discriminator is further optimized to enhance its ability to tell which one is fake and which one is real. So this process of working together and working against each other goes on and on and on. After many iterations of training and optimization, finally, the discriminator would no longer be able to tell which one is fake, which one is real. At this point, the generator is considered to be able to confuse the discriminator and generate real-looking data. At that point, we see it's reached the Nash equilibrium. However, a standard GAN model can be flawed. Let's take a couple of examples. The first one is called mode collapse. And in this example, the task is to generate all 10 digits as the top row shows. However, a standard GAN model can only generate 1 digit, no matter what the input is. Well, the second row of pictures show that, well, a digit kind of look like a 6 is generated. No other than that, no one other than that. So we call this mode collapse because no matter how you vary the input, you can only get one result. That's not ideal. And second issue is distortion. In this example of 4x upscaling in both directions, the input is actually 1/16th size of the top left one. So imagine, and then the task is to scaling it up and to get results like try to get result like the original picture. So showing on the left are the ground truth high resolution pictures. That's desired result. On the right-hand side is actually state of the art. It's a model called ESR GAN, which won the 2018 first prize in the European Conference on Computer Vision. So even with this state of art, you can see that the stripes on the zebra legs are actually distorted a lot and not even close to the original. So the faithfulness, fidelity is bad. So how to alleviate those problems? So we start working on this and try to think of ways to improve it. And we have designed a new innovative GAN model. Both its architecture and the algorithm is quite innovative via the so-called latent space regularizations. So I'd like to very briefly explain using a few images to tell you what's the latent space optimization mean. On the left side is a 3D surface. In the middle is actually the latent space, the default one. And the task is to have some samplings in this latent space and then reconstruct the 3D image. Well, what we humans is best at doing is do uniform random sampling. So in this case, we do the random sampling in the latent space as shown in the middle, and then reconstruct the 3D surface. We got the dots showing on the right-hand side. Those dots are overlaid on the original picture. So this is what we get. In some places, the reconstructed dots are dense enough, like around the leg, but in other places, like the head and the face, the reconstructed sample are really sparse. So that means those areas are underrepresented, and the reconstruction is not good at all. You may not get the head or face in this case. The generator is actually trapped to a local minimum, leading to a suboptimal reconstruction. Now, we want to change that. So we optimize the latent space a little bit, and then try to do the same process of reconstruction. Now, in this optimized latent space, again, the sampling is uniformly performed. Now, we get the reconstructed points and overlaid on the original picture. We would see a much more reasonable distribution of the reconstruction. And now you see the face and the head are more represented. So the Agora GAN model significantly outperforms the state of art as a result of this new optimization GAN model. Let me show you some pictures. Again, on the left side is the 2018 first prize winner of the European Conference on Computer Vision. We just saw that. And on the right-hand side is the Agora model. We can see that the structures are much better and clearer, and also more faithful to the original ground truth. Take a look at another picture. In this one, the patch images on the left is the high-resolution truth, ground truth, which is desired. And in the middle is the result of the state-of-the-art ESR GAN. Again, we see that the cards are not restored appropriately. And there's no detail, and the structures are not right at all. On the right-hand side, we start to see that there are cards and some details of that. This is from Agora GAN model. One more picture for showing all those methods. On the leftmost, we have seen this conventional bicubic-based interpolation for 4x upscaling in both directions. And on the right-hand side is ground truth, which is desired. So we get a result much closer to the ground truth, and also it's sharper. In some places, it's sharper than the ground truth. And take a look at some quantitative measures. And the industry or the literature has been using like PSNR, structure similarity, and also perceptual index to measure the quality of the super resolution method. And PSNR and SSIM are two metrics which are regarded as the larger the better. The perceptual index is actually the other way around. The smaller, the better. And we have been testing our algorithm and compared it to the ESR GAN using some commonly used test data sets. Across all those measures and across all those data sets, we outperform state of the arts. And one information here is that the literature usually considers the PSNR and the structure similarity and the PI contradictory to each other. So, which means that most algorithms can only achieve, you get better PSNR and structure similarity while sacrificing the PI, or the other way around. If you want to get better PI, you probably sacrifice PSNR and structure similarity. Our algorithm actually improve both, fortunately. So based on this new optimized algorithm, the next challenge is to try to reduce this model so that it can be run on mobile devices. As we stated earlier, this is extremely challenging as well. And we need to find the optimal trade-off between the super resolution effect and also the computational load. So the compromise is that instead of like support up to like 4x upscaling in either direction, now we make the mobile version support 2x upscaling in both directions, which means the SR result would be 4x as large as the input. And also we minimize the computation and still be able to obtain significant detail and sharpness enhancement without causing very obvious artifacts such as the ring we showed earlier in the sharper iOS scalar. Now first, let's take a look at the model size, the way we try to achieve smaller model. Here are a few classic deep neural network models. VGG16, ResNet 101 and Google's MobileNet version 2. MobileNet version 2 is a small model which is used to recognize objects for object classification on mobile devices. And it's only less than 10% of ResNet 101, the number of parameters. This is one of the metrics to measure the complexity or size of the model. So 3.4 million parameters in MobileNet version 2, and it's been usually used as benchmark in the literature. And to compare our model with MobileNet version 2, we were being able to make the Agora SR model extremely small, which is less than 1% of the MobileNet version 2. And computation-wise, it takes less than 1 gigaflops per frame for 480 by 360, 480 by 360p, upscale to 960 to 720. And a quick look at the result. On the right-hand side now is 2x upscaling in both directions using our mobile SR model, which is significantly sharper than the left-hand side. And also take a look at this. And in the middle is Agora middle. On the left is the iOS normal scalar. On the right-hand side is the iOS sharper scalar. And our model is the sharpest among those three. And the artifacts, the ring artifacts is less than the sharper scalar of the iOS version. I'd like to show you a video on this. So the vertical red line wipes through from left to right, and it clears up the blurriness. So the water and the stone, mountain, text are all enhanced significantly using this mobile version of our model. And I can quickly, one more time, and it stops somewhere. So look at the stone. Look, if I stop here, the left-hand side is the result after our SR. The right-hand side is the result using conventional scalar. Now let's move to the next topic. It's for video coding. And again, we're being able to make use of deep learning to achieve significant coding gain. So video coding is actually is a core for our RTC application, and it's actually the backbone for all the RTC applications, right? So there have been many work trying to achieve more coding gain, and conventional method is trying to reduce the redundancy via the rate distortion optimization. The distortion is usually measured by PSNR or a similar metric. The problem is that the PSNR doesn't always correlate well with our human visual system. So after optimizing PSNR, it doesn't mean you're optimizing the perception of the video quality, which results in pictures with, for example, more blackness in some areas than other areas. So the whole picture is actually not, the quality of the picture is not uniformly distorted or degraded. So perceptual video coding has since been researched a lot in the industry or in the research community. Now the goal becomes to reduce the perceptual redundancy instead of the PSNR or traditional rate distortion optimization. So the perceptual distortion is highly content dependent. and it's very hard to quantify, and it's also highly subjective. So neural network may provide a very good solution on this, like human visual-based properties to quantify the subject perceptual distortion. And the idea is to find the just noticeable distortion. So JND, just noticeable distortion, is a threshold under which the distortion cannot be perceived at all, above which the distortion will be visible. So the task is to find this JND value, and the SS is content dependent. So need to label a lot of JND data with a very wide variety of video content as a training data. And we know neural networks depends on a lot of data for supervised training. So, and also we find that even given the JND, if you ignore the video encoding process, there could be problems. So for example, the video encoding usually achieves compression through quantization. So the quantization loss has to be taken into consideration. Otherwise, we would get visible artifacts as shown in this picture. On the right-hand side, carefully looking at the cheek of the lady, you can see the blackness, even though this method claims that it just applies the JND to the encoding. So it's not really JND in this case. The reason is not because their JND is not bad, is bad. It's because they didn't take into the encoding process into consideration. So those two parts, the JND and video encoding, don't cooperate well. And the Agora PVC model, then we combine the JND with the encoding quantization loss. And also we decide the JND thresholds collectively in the transform domain. And meanwhile, again, we have to make the model extremely small so that it can be executed in real time in mobile devices. So we performed the supervised learning offline and using a lot of labeled JND data as a training. Finally, after it's trained, we adopt the inference DNA model on mobile devices. Now, we will be remove the artifacts we just shown. On the right-hand side is Agora result. On the left-hand side is an existing state-of-art, which I just showed, which has blackness shown on her face, on the cheek. And some result. We did some double-blind tests. More than 20 subjects evaluated 180 encoded clips. 90 of them is PVC turned on, and the other 90 with PVC turned off. And we measure the DMOS, the difference of the MOS score. MOS means mean opinion score. It's a subjective evaluation score. So DMOS is defined as the MOS when PVC is on minus the MOS when PVC is off. In the literature, the DMOS degradation of less than 10% is usually considered acceptable. And so all those 180 clips, we encoded it as a typical quality and bit rate that's for mobile RTC applications. And the end result that the average degradation of our JND model is less than 1%, so far better than the 10% regarded by the research community. And the average bit rate we saved is more than 23%. The 90 clips we have been using, including not only the typical thing for RTC, but also a wide variety of other clips commonly used by standard committee to develop standards. So we also find that for typical RTC scenario, for example, the meeting with head and shoulder, the bitrate coding gain can be even more than this. And now let's look at our PVC neural network model size. Let's compare with MobileNet version 2 for lack of direct reference. So still it's a good reference. Our Agora PVC DNA model is actually 0.1% of MobileNet version 2. So it's even smaller than our SR model. And again, for computation, it's less than 1 gigaflops per 720p frames. The processing power is minimized. Is thus minimized. So I like to show a live demo. Let me. Okay. A little bit hard to control here. Let me use lowest quality. So quality 1 is the lowest quality. So in this demo, is actually encoded and decoded and then displayed. On the right-hand side is the real-time bit rate. So the digits there showing the it's 500, 600 kilobits per second coding bit rate, and the red line is illustration of the bit rate. And when it's red, it means the GND is off. The perceptual vision coding is off. And let me try to move like this a little bit to make the content a little bit more interesting or typical for like a meeting. And I like to now I can turn on the PVC. The green line now is represent the new coding bit rate, and the digits is about 300, 400, or even 200 range. Let me turn it off. It jumps up immediately. So could be like 500, 600. So sometimes we save 30%, sometimes even like 50% coding bit rate. And also pay attention if you can notice the difference of the picture quality. On, oh no, off. On, off. So in our blind tests, very few people can tell the difference. Actually, yeah, we ask each subject. They normally very interesting. We ask them to like watch no more than for 20 minutes on those clips. They tried very hard, and each one tried to beat our system. Like they spent 40 minutes on average, tell whether it's they can't tell which one is which or which one is better. And yeah, so I previously reported the like DMOS score. That's the result of blind testing. So anyway, and actually there are other input files. So for like this one, yeah, it's about. Let me turn it off. When it's turned off, it's like sometimes, yeah, a scene change. The bit rate is larger. When turned off, it's usually go under 1 megabits per second. When it's turned off, it's higher. It's normally above 1 megabits per second. Turned on, the bit rate will be lower. So we have been able to make use of the AI algorithm to achieve more coding gain, which we're pretty happy with at this moment. And let me go back to conclude my presentation. So deep learning has been very helpful in many areas, RTC, almost all areas. And it is extremely challenging to design the deep learning model that is small enough for mobile devices because of the high demand for computation, and also the power consumption could cause heating issues. So during the process of development, even when there are a few times, even when we thought we've already been much better than state of art in terms of this model size, it turns out that after running like 2 hours continuously on, together with our SDK, the device would become very warm, and then we have to go back, try to reduce the model again. But the dilemma is that you still want to keep the effect of the AI. And yeah, we are committed to make a full use of deep learning to provide the best quality of experience for RTC. And yeah, there are more to come, like for image restoration, style transfer, audio processing, and even for network transmission, like channel estimation, the congestion control, all those things. Yeah, we will have results to report to the community at a proper time. Thank you very much.